So scientists think a little differently than the general population. And one of the things that describes how we think is the scientific method. The scientific method is not a rigid procedure that says, okay, we're going to do this, and then we're going to do this, and then we're going to do this. It's more like a guiding philosophy of how to go about investigating things. We learn by making observations and then doing experiments, trying stuff. The ancient Greek philosophers emphasized reason. And so they would sit around and think they would think about stuff. And so a lot of their philosophies ended up being wrong because they never tested them or anything. So we don't do that. Here's an overview. Pictures are often good. So here's the starting point. The starting point for scientific investigation is that we make observations. And the scientific method can be applied to everyday life types of problems too. We make observations, and based on what we observe, we're going to make some sort of a hypothesis. Well, I think this is why it's going to happen. And I wish I could come up with a different example, but I'm just not able to while I'm talking right now. So I'm just going to give you a very weird, slightly gross example from my own personal life. Okay, so I have five sons and a daughter. And the youngest one is going to be 5 next week. And so the bathroom, there's often liquid on the floor in the bathroom. So the other day I go in there and there's this big puddle on the floor in front of the toilet. So observation, there's liquid on the floor in the toilet, in front of the toilet. No? Okay, well, then we have some questions about this. What is it? Where did it come from? How can we make this stop happening, right? So we develop a hypothesis, which is an idea, just a possibility of what we think might have happened. So a very far-fetched possibility is the neighbor's dog came in through the cat door and peed on the floor in my bathroom. Not very likely, right? But we could test it. Someone spilled a glass of water on the floor. Possible. Andrew got up in the middle of the night to go to the bathroom and forgot to pull down his pajama pants. Possible. If you pee with your pajama pants on, it just runs down your leg, makes a puddle on the floor. I've seen it happen. Okay, so we have this observation, and then we have a hypothesis. From the hypothesis, we don't just decide, oh, yeah, that's the most likely one, that's it. We test it. So we test the hypothesis. We test the hypothesis by doing experiments. Now, when you think of experiments, you probably think of, test tubes and boiling flasks and all kinds of crazy lab stuff. But an experiment is just, you think about your hypothesis and you say, well, let's see, if someone spilled their cup of water in the bathroom, an experiment would be, well, if I wipe this up with a paper towel and look at it, it should look clear. And if I sniff it, it shouldn't have any odor. So that's an experiment. You wipe it up, you look at it, oh, it's kind of yellow. Careful sniff. No, not water. Okay, that disproves your hypothesis. The hypothesis of a spilled cup of water is wrong. So the hypothesis, you go back to the hypothesis and you revise it. You say, oh, okay, well, let's get rid of that one. Let's go with the Andrew wetting his pants one. And so then we look at the results of that test, that it was kind of yellow and smelled kind of like pee. It's like, okay, that supports the hypothesis. We usually don't settle with one experiment. We do other things. So how else could we test that hypothesis? We could check the laundry. Okay, so if we go to the dirty clothes hamper and we find wet pajama bottoms belonging to Andrew, that will support our hypothesis that he peed on the floor in front of the toilet. Like, you were so close. Actually, I discovered that puddle by stepping in it the next morning. It was lovely. What if we go to the laundry room and the dirty clothes basket and there are no wet pajamas in there? Does that disprove the hypothesis? No. Because how many almost 5-year-old boys do you know that always put their dirty clothes in the hamper? Right? So then we go looking around the house to see where he may have ditched them. And maybe we find them, behind the door in the bathroom. Okay, but you get the idea. So the hypothesis gets tested, and the result of that experiment either confirms or causes us to revise the hypothesis. Now, after experiments have been confirmed many, many times, we may end up with a law, or we can end up with a theory. And these also undergo continued testing. So now that I've given you that weird example, we'll go through the slides here. First step, observations. Some of these you can do just by looking at them. Others, we need to use really sophisticated, sensitive equipment. Usually we're measuring something or describing something, some aspect of the physical world. There's this other example here. I'm not going to do that because I gave you a more interesting one. Observations lead to the formation of hypotheses. A tentative explanation. I think this is why this is happening. I think this is what's going on. A good hypothesis is falsifiable, meaning it could be proven wrong. It's really hard to prove things are true because maybe you just haven't found a way to disprove it yet. Okay? So, a good hypothesis is falsifiable. Yeah, I don't have anything else to add. And we test these hypotheses with experiment. Scientific experiments are highly controlled, and we do them in a way that is very specific and with an aim to either prove or disprove the hypothesis. If the experiment shows that the hypothesis is wrong, we may just get rid of it entirely, or we might modify it. If we modify it, we got to test it again. So we go around in circles. After we get a number of similar observations, that may lead to the development of a scientific law. And a law is not like a civil law, which is something that needs to be obeyed. A law is something that just says what happens. And it predicts future observations. So you've heard of the law of gravity. So what does the law of gravity tell us? What goes up must come down. Things fall, right? So law of gravity, what does it predict will happen if I let go of this marker? It's going to fall. Sure enough. Every semester. Does it explain why? Nope. Interestingly, scientists still do not fully understand gravity. And it's still kind of a mystery. Gravity is pretty complicated. But we do understand that things are going to fall down. Things do not fall up. But the scientific law of gravity, says what happens, doesn't explain why. Another one is the law of conservation of mass. That whole example is in the textbook, and you might want to read about that. But these laws are also subject to experimental testing. So we test those as well. We test everything. Hypotheses may lead to scientific theories. A theory is different from a law because a theory provides an explanation. A theory says this is why it happens. This is how it happens, not just what happens. These theories often lead to predictions of behavior that are way beyond even the imagination of the people who originally came up with them. As advancements come along and new discoveries, we realize, oh, wow, look at this. That theory predicted that this would happen, and here we have the technology to see it. Theories are also subject to experimental testing. So here's just contrasting laws and theories. A law states what happens, comes from observations, and we can prove laws to be false. Theories try to explain why. That's the main difference between a law and a theory. Law says what happens, theory says why. These arise from hypotheses, whereas the law comes from observations. Theories can also be proven false. Theories are as close to truth as science can get. So you may hear somebody, oh, well, that's just a theory. No, in science, a theory is a big deal. This has been tested repeatedly until nobody can come up with an exception to it. Does that make it true? No, we cannot prove things to be true in science. Just, a little disturbing to some people. All we can say is, as far as we know, this is true. Nobody's been able to come up with an exception to it. So we're taking this as true for now. That's what a theory is. And of course, there are people out there trying to find exceptions. And that's good. These kind of out there people are like, well, you say that's true, I'm going to prove you wrong. If you can prove the theory wrong, then the theory needs to be modified. Yeah. The theory needs to be modified. And oftentimes those situations where someone has found a situation in which the theory doesn't work anymore, that's where big advancements have been made. And so it's really helpful to have those skeptical people saying, I don't know, I think there's some situation where that's not going to work. Okay, you go try that. And they do. But that's just, basically how these things work. So, as an example, here are 4 statements, and we need to classify each of these as an observation, a law, or a theory. So, this first one. When a metal is burned in a closed container, the mass of the container and its contents doesn't change. I've heard law and theory. I would call that an observation. That could become a law, but that it would have to be repeated many times. So I would classify that as an observation. B, matter is made of atoms. Theory. Why is that a theory? Well, can we observe atoms? Can we directly observe atoms? No, we can't. They are too tiny. Okay? So it's not an observation. Is it a law that states what happens? Not really. It's more of an trying to explain why. Matter is composed of little teeny tiny particles. Okay, statement C. Matter is conserved in chemical reactions. Well, first of all, what does that mean? Because we didn't follow up on the example. Matter being conserved means that whatever you start with, you end up with the same amount of matter. It is an observation. And see, I wouldn't ask you these on a test because I don't think they're straightforward enough. This is similar to part A, isn't it? When a metal is burned in a closed container. But that was a lot more specific, and that was like a one-time thing. And this is, matter is conserved in chemical reactions. This is more of a generalization, a stating of what happens, which would be of what happens, not why, a law. Okay? When wood is burned in a closed container, its mass doesn't change. That's going to be an observation. Okay, any questions? Are atoms real? Okay, we do have the technology now to get fuzzy pictures of atoms. And so this is a Japanese kanji characters for atom, written with individual iron atoms on top of a copper surface. But you can see the image that we're getting of them is pretty fuzzy, right? They are not actually shaped like these little cones. And this is from a very, very sophisticated instrument. What's even more impressive to me, though, is that they were able to move the atoms around and actually make the kanji characters. But that's just kind of cool.